Let's look at one more example where things are not very straightforward, but not too difficult either. It's a piecewise function, so let us say minimize x in R1, f of x, where f is actually one of 3 or 4 functions, maybe minus x1 cube if x1 is less than 0, x1 cube if x1 is strictly greater than 0, and x1 is less than equal to 10, and 100x1 plus 100 minus x1 square otherwise. So f is not just a simple function consisting of sums of simple functions, but it is actually a combination of 3 or 4 or maybe more functions. So again, depending on where x1 is, we may have to evaluate different smaller functions to find the value of f. In many design problems and industrial applications, the function is actually not even available as an input. It might be a complicated computer code, so where f is the value, or let's say f evaluates the given computer code, which could be potentially thousands of lines. So imagine some computer code which mimics the functioning of a chemical reactor or a nuclear reactor, and we would like to find the best possible way of running that piece of machine, and we have several different settings over which we can try to optimize the process, but we don't know the output as a function of input, as a simple mathematical function or even a slightly complicated mathematical function. You can imagine that it's a very big piece of simulation or some differential equations being solved to model the behavior of a complicated machine, and all we have is this computer code, which has a lot of for loops, if loops, conditions and jumps and so on and so forth. So how do I choose an input setting so that my machine is working in the best possible way? That means I'm trying to minimize some function f. So here I don't even know whether f consists of trigonometric functions or some integrals or some linear and quadratic terms and so on and so forth, right? So f is just a box. So f is just a box where if you provide some value of x, you will be able to see the value of fx. Okay, so we don't really care. So most generally in unconstrained optimization, we don't care the functional form, what the functional form of f is. Okay, so what we are given is some black box, and if you give this black box an x, it will magically spew out the value of the function at that point, and we would like to find the x where f is minimized. Okay, so this is the most general form of unconstrained optimization, and we will see that this doesn't give us it's slightly difficult to optimize because I don't know the shape of the function. Okay, so to find minimizer of f, we need something, we need some knowledge about f. So merely knowing the values of f at a few points may not be enough, but in practice many times that is the only input that is available to us. Okay, so let's look at some very preliminary methods of going about finding solutions to unconstrained optimization problems. Okay, so the most obvious way, and what most people would actually try to do if they have not done this course, is to make a plot, and especially for one-dimensional functions. So if I have a one-dimensional problem, you can try plotting it. But that may not always be very easy. So if I go back to my earlier examples, then example 1 is somewhat easy to plot. There's a linear part, and then there's a plot which goes up, a part which goes up and down, and I can take the sum of these two and try to get a rough plot and see how the function behaves. Drawing a plot for two-dimensional functions is somewhat more tricky. We will see in possibly the next lecture how this can be attempted. For a function like example 3, plotting the whole function is going to be, I think, far more difficult than actually finding the minimum. Because plotting really means that you are able to find the values of the function at all possible points, and once you know the function value at all possible points, then it is sort of easy. This function will take a long time even on a computer to plot, because for every x1 I need to first evaluate an integral and then make a plot. So plotting works for only simple problems. So if you are able to make a plot of your function, then you don't need actually any other sophisticated tools. You can live with that plot and get a reasonable answer, and that might be the right approach actually. The second approach, again, which is quite practical but may not always work, is to just evaluate the function at several different points and pick the best. Extremely ad hoc and no guarantees. In fact, it will almost always not work. Okay, so again, you would try to do this if you are not really interested in optimization, but you just want something better than what you currently have, and you have not much idea of how to go about optimizing the function given to you. Also, many times, the function itself is so complicated that you can't do anything sophisticated algorithmically or mathematically with it, and then this might be your ultimate last resort sort of a thing. Whenever you can't, if you are totally helpless, then you can try doing this, but otherwise not. And then you can tune the procedure in #2 and be smart about number of points. But again, this is still quite ad hoc, little less ad hoc than number 2, but still pretty ad hoc and not guaranteed to work. And you can also try some randomized methods. So instead of picking up points by thinking about them, what you can just do is use a random generator so that you get a different point every time, and then let pick the best out of those randomized points, and you get a lot of heuristics out of this, depending on how sophisticated you are in randomizing and learning from the previous samples. So heuristics like genetic algorithms and simulated annealing and taboo search, they fall under these methods. So you can so they are less ad hoc than number 2 discussed above, but still they don't guarantee much, and many times you have to generate many points before you are confident that the solution you have is actually good. So we will not be studying any of these 3-4 methods that we have listed on this slide. Rather, we would do something a little bit more structured and systematic. So what will be those methods? We will cover in the next lecture. For now, we will stop. See you next time.